Welcome to week 7 of developing a UAV drone swarm. If you're new to this series, I'm trying to develop a humanitarian UAV that can carry up to 5 kilograms worth of payload, which can help feed people in dangerous areas or just deliver anything basically. It will be a VTOL drone, it will be fully modular, and we are going to do everything to make this as cheap as possible. I'm documenting everything every week of this on YouTube on this channel, and we're at week 7 right now. Based on previous videos, we now got a team of like 15 people that are actively working on the development of this drone. So there's a lot of stuff going on. Today I'm gonna go over how we are going to build the flight computer, because we did a lot of work in that department. We even have a really cool name. So introducing Navius AeroCore. This will be a modular flight computer that will also be sold to the public. It will be very affordable. It will be able to be used with ardupilot, and it will also be modular, meaning that you can add extensions like a better receiver, for example, or an entire module on offline navigation for when the drone is being jammed. And I want to go into how I'm planning to do this by using computer vision and edge detection and stuff like that. I will also be looking at how to structurally build the plane. So all in all, very interesting. Enjoy the video. Hi there. We are working on making a flight computer for the drone. Of course, we want to do a lot of cool stuff with the flight controller as well. It needs to be cheap and it needs to have a lot of cool stuff on it. This means that we are considering selling this flight computer as a standalone thing so that you guys can also use it in your own drones and own UAVs or something. But I'm getting ahead of myself. First, we need to determine what do we need the computer to do. First of all, it needs to be modular. What do I mean with modular? I'm imagining something like this. You have the main box. Inside of that will be the flight computer with only the basics that it needs to be a flight computer, to control a quadcopter and to control a regular plane. On top of the box could be a little connector like that, so that a module can go on top of that and it can fit on the connector like a Lego brick. Then on top of the module, we could have another connector, and you can just repeat the whole process over and over again. What this means is that you only pay what you need, which is kind of a goal for Navius. Why'd you buy a very expensive flight controller when you only need to fly? And maybe you also need it to work with like ardupilot, for example, and not all of the other nifty stuff that you might get with a flight controller that you can buy online. So for example, the main module will be able to control flight like any drone. Along with that, if we imagine that this is the side of the main module, you could have like little side inputs or side connectors, which you can then use to attach things like a specific receiver. Obviously, you need a receiver to fly, so you would probably get a default option delivered with the computer. But if you want an even better receiver, you can just buy one on the website and plop it on what you have. Now, this could also be done with different things, and it can also be done for the modules. For example, an input for a camera, stuff like that. The receiver and everything to just fly regularly will be done in this box. Then on the other box, we can do stuff like offline flight, which I wanted to be able to do. So let's add that to the list. Offline positioning system. I will go into how I'm imagining this, but what I needed to do is it should not be dependent on radio signals or GPS. And what does it need to do? It needs to understand where it is, what coordinates basically. It needs to be able to tell the altitude, and it needs to be able to tell the speed, which is just some calculations if you have the other ones. Now, of course, it needs to be cheap. So for the offline flight, for example, instead of LiDAR, you could use radio thingies. I forgot the name, like sonar stuff. But we will get into that later because they have a limited range and we don't want it to have a limited range. It needs to be able to fly at a high enough altitude, so it's not limited in any way like that. The main module also has to be capable of using ardupilot, which is open source, so we can change up some scripts and add our own parts to it. But especially right now, it saves us a lot of time to use ardupilot, which if you didn't know is like an open source software where you can do mission planning and stuff like that, which is amazing, of course. This is what we want for now, and we will have more space for new modules in the future. So now, how will we start building this thing? First of all, let's ignore the modular part, because that's just for the future, okay? The offline positioning system is really cool, but also for the future. But I thought we do kind of have to think about it, and it is really cool. So guys actually found a way to do this. I hope it is gonna work in practice. We're working on it, but I did some tests and it worked kind of. Okay, I'm gonna show you that in a moment, but this is really nice. Now for the main module, Xenos already started making a PCB, which is the one that you saw in the intro. Now, this is not precisely or accurately what the PCB will look like. I just really wanted a cool animation of this for the intro and for the thumbnail, and it just looks cool, let's be honest. But this is heavily based on the real thing. There's an actual CAD drawing, but I don't want to show it on YouTube for now. So this is basically the gist of it, and I will go over what everything does and what it will be capable of like this. Now, to be fair, I might be very wrong on which chip is which, so I just guess it because I know what chips will go on it. I just don't know on this exact configuration which one's which. First of all, we have the MCU. Let's just go ahead and imagine that this is the MCU, okay? The MCU stands for the Master Control Unit. We are going to either use a Raspberry Pi 2040 processor or a Jetson Nano. These are pretty strong processors. The Jetson Nano is stronger than the Raspberry Pi one, I think, but it's also a lot more expensive. So we're going to try and do it with the Raspberry Pi one. It's way cheaper. And also, like I said, we have the modular thing. So we could have another module for like upgraded graphics processing unit, GPU 4090 in there, you know, just kidding. So obviously the MCU will just think, basically, kind of like me or not. Then the next thing, let's just say this is it. The inertial measurement unit, aka the IMU. Oh, I can draw on Blender as well. So this thing has a gyroscope, a accelerometer, and a geomagnetic sensor. Of course, these things are just pretty much necessary for a flight controller to have, and they're also pretty damn cheap. Now, the geomagnetic sensor is basically a compass, which is also going to be very useful in the offline flight, so that's pretty great. Now, we were considering using an optical flow sensor, which is not on the board, of course, it's somewhere externally. We can imagine that it's this right here. This is an optical flow sensor, all right? What it does is it kind of looks at the ground, and it can like detect terrain. And it can also very accurately detect changes in the terrain that is right underneath it. But of course the drone moves, so the drone goes that way and the terrain goes that way. And the optical flow sensor can detect that, and with that it can calculate the speed and movements, which most drones use to have a good position hold to stay in the same position. But the optical flow sensor also depends on having LiDAR because it needs to know the altitude that you're at. Now, there's an issue with that because, first of all, LiDAR is expensive. Now, let's imagine this is the LiDAR. It shines a laser at the ground, and then this camera perceives when it hits the ground, I think, and then it knows how long it took, so it knows how high it is from the ground. Now, LiDAR sensors are a bit expensive, so you could use the ultrasonic sensors, which is practically the same thing, but then it uses radio waves, no sound waves, my bad. Listens to like the echo coming back to this sensor. And this is like way cheaper. It only costs like $2, but it also has less range. And the LiDAR has a 12-meter range, and this one has like a maybe 4-meter range, maybe less if you want it to be accurate. So we might need to do something else for this. Now we have a plan for that, but I'm gonna warn you, it's very high tech and it's a bit ambitious of us to give it a go, but I'm actually convinced that we can. Not everyone is as convinced, but it's just very exciting, so I'm going to show you that in a moment. But with that, we don't need any of this basically, although we might still keep the cheap ultrasonic sensors because then at least we can still like land in VTOL mode and stuff. But we don't want to spend like money on LiDAR when it can only do 12 meters, same with the optical flow, because we will be flying higher than that unless we are landing, but you're not landing and taking off very often, especially if we're planning to drop packages whilst in flight. So then, for example, if we want to use it on a van and like launch the drones from a van, you could also just have an external thing that sees the drone and tells the drone where it's at. So then this would still be obsolete. Next thing is LED controls. Now, I'm not sure, but somewhere in here you have connectors for up to 512 addressable LEDs. Now, of course, these are not 512 connections, so you would have to bring it to like a breakout board, I think. But there is a chip somewhere here that is capable of controlling 512 LEDs, and they're RGB. Now this is necessary for like the legal lighting requirements on an aircraft, and this also counts for future projects. We might still be able to use this flight controller because yeah, this will also be good enough for like light shows and like smaller drones, for example. Now we also need to control servos, so there somewhere in here is a connector that I think it's a chip, so let's just say this is the servo control, and it can control up to 12 different servos. And I think somewhere here is like the connectors for the servos. This is important for us because of course we will have wings, and wings have control surfaces for like flaps and stuff like that, so we need to control them, and we will definitely be using servos for that. So having 12 servos gives us a bit of like room for things like Bombay doors and stuff like that, so pretty nice. Now, I don't know which chip I missed here. This might be the LED control one, or it might be the radio link, which I assume would be going to here, and there you can like attach a radio. I might be wrong though, but for now at least, we will just have a random radio receiver for testing purposes, but this will become something modular, so that's nice. So this setup, if we would include the optical flow sensor, the LiDAR, the radio link, and the ultrasonic sensors, and then even after that, if you overestimate the price, this entire thing will cost 120 USD, including manufacturing, which I guess it's cheap, but here's the thing. We're probably not going to use the optical flow. We're not going to use the LiDAR. Now, I don't know if I'm allowed to call it sonar, but we're not going to use it. Or actually we will, so I mean, that's $2. But the LiDAR and the optical flow sensor in total cost like, I don't know, $38. So we would not need all of that, and that would bring this price down to like 90 or something, which is a lot cheaper already. Now, the only thing that we still need to include in the base version is a regular GPS antenna and a barometer to understand the altitude a bit better. So this is basically the plan. Now, of course, we also need ESCs to control the motors. I guess we can also make that a module so that you can control quadcopters with other types of copters. I don't know. But that's all electrical stuff that I will not think about because I'm bad at it. Now, all of this work, making this, picking components, everything is done by Xenos. So fat ass shout out to him. Now let's go ahead and think about the offline positioning system, because I bet that you guys are like, how the hell are you planning to do this? Because you're right. It's very hard to do this, and especially on a budget. So I did talk with Jonathan, and he was also a bit skeptical, but sorry, Jonathan, I'm still gonna try it. It's apparently something that is actively being researched, and it's really like a new development. First of all, we need a camera that will look directly to the ground. So imagine this, the ground, there's a couple of trees, there's a road here and there, some bushes, you get the point. Now, actually, I realized that drawing this in Blender is not a good idea because I actually made a flow chart for how I'm imagining this, okay? And I also tested it with some GPT-4 scripts, but I'll show you that in a moment. The first thing it'll do is save coordinates, speed, etc. So when the GPS stops working, it'll know where it stopped working. So let's say the red dot here is where it stopped working, and the line is the predetermined flight path. Because you need to like tell the drone before taking off for this to work. Then it needs to go ahead and determine what data to load in for the positioning. Because what I'm imagining is that it looks to the ground and then it compares what it sees to data from like a map. For example, here's a random place in Ukraine. If this is what the drone sees, it can take a picture of this and compare this picture to a picture that is stored on the drone with embedded geolocation. So then it'll find the closest picture to it and assume that that's the one. And then it'll look at the embedded geolocation of the picture that it was similar to, and then it knows where the picture is from and it knows where the drone is. So the thing is, how accurate can we make it without overloading the processor? Of course, we can like take pictures of every small detail like this, which means that it has smaller portions to match to, which also makes it harder to match because images will not be very distinct from each other. But it will also be harder for the computer to look through hundreds or thousands of images. So that's the thing. I think if we have chunks of like 30 meters, then you can have 30-meter accuracy. And if that's something like this, I don't know, it's way easier to tell similarities between images like this than it is from images like this, because there's multiple places like this in the world. So we kind of have to determine like how big the chunks should be of images. And then it needs to understand which images it should look at, because it cannot look at the entire world. It will just overload the processor. So if we can make like a view like this, and it can load in all of the images within this range, so that if it goes off course like this, it'll still know where it is. And if it goes straight, it'll also know without like having to load in everything here. So once it determines what it needs to look through, the computer looks at the camera of the drone. For example, it'll see something like this. And then you can apply edge detection, which is kind of like it looks at dark spots, it looks at light spots, and it makes like more distinct images. It's like making something super contrast, basically, for the computer to more easily tell differences. And it also makes it like a smaller file size, I believe. From there, you can go two ways. One way is that you store this image so that you have an updated map of where you can fly. I'm imagining like a cloud service where everyone just uploads their maps of where they flew automatically, unless they disable it. And that means that it can more accurately position itself above those locations, because obviously during a war zone, this might just be a crater in a day, you know? And then it'll just take a picture of that and upload it so it's more accurate, because from Google Earth, for example, you can only see like imagery from 2022 or something. But if we can have a whole drone swarm fly over a place and automatically map the place as well, that is useful for a whole lot of reasons, also for just mapping missions. Now, after you added the edge detection, you can also find the most similar image in the data that we defined here. So it'll look at all of these chunks and see what this looks most similar to. When it found the one, it can find the geolocation in the metadata of the matching data, like the matching image. And then it can create a map like this. Now you can repeat this process at like 10 frames per second for a more accuracy understanding of where you are, because there's less likelihood of failure if you take the average of like 10 pinpoints per second. Now you can also like increase the accuracy or determine how accurate it really is by looking at if it's even possible, because it will have an onboard compass and stuff like that. So we can tell if it's like logical or not for it to be like 10 kilometers further than it should be. And then you can instantly like ignore that pinpoint based on that. Now you can go two ways. You can find how far a coordinate is above sea level, so like the ground, and then you can determine the height above sea level of the drone with a barometer. Then you can deduct the ground height to determine the altitude above ground. So then that's also an issue that's solved. Now the only thing is that you need to understand the weather data, so we can have it like go to the drone via radio, and then when the drone gets jammed, it's very unlikely to hugely change out of nowhere, so this should still be fairly accurate. Now with this, you can also calculate the speed of how fast the drone flies, because you can just measure the time from this point, for example, to this point, because you will get the actual coordinates. So then you can very accurately tell how fast you're flying and how much distance you traveled and stuff. Now based on that, you have the output, altitude above ground, speed, and geolocation, along with an up-to-date terrain map for future use. Now I think it's a genius idea. I mean, I kind of came up with this flowchart myself, but not fully, because Jonathan did tell me about like research going on with edge detection and stuff like that. And I used AI to actually try and do this in practice. So I will show you real quick. So what I did is I took an input like this, and I took this from Google Maps. So I made like an animation and I exported it in a like frame by frame way like this. So as you can see, it's flying above from some terrain, and it's like every image has the geolocation embedded. And this is at like 120 meters height or something from the ground. And as you can see, it's just trees. It's not very distinct, so you would think that this is a pretty good test. So then I have a script made by ChatGPT in Python where you can apply the edge detection and change up the threshold. And you can see like the before and after. And as you can see, you can like adjust it a bit till you have a very good map. And then you can click apply to all images, and it'll change all of the images inside of the folder you selected. And it'll have some output looking like this. And it kind of looks like this when you play right through it. And as you can see, it's pretty good. So this part is a bit less detailed. because it's worse quality. So I took some of those images and I messed it up a bit. I drew some stuff on it here and there, drew a lot more on it, drew even more on it, even applied like some color filter, see if that would make it any different. Because of course in the real world it will never be as like the same thing as on Google Maps or Google Earth. And then I put it in my other scripts that I made with AI, the image geolocator. So what you do is you select the data and I will select the bad input and then you click find similar images. And there we go, pretty quickly. It has already located every single point on the map from start to finish. I also have an older version of the script which shows you in detail like which image is similar to which image. Most of the time it is 100% accurate and sometimes it's like 5 frames off, but of course in this setting like 5 frames off is like a small difference. It's still pretty accurate location. So that's really cool that that works, but of course it's still just Google Maps. We need to know how reliable this is. So I showed this to Xenos and he will be talking to a few other people and some people also joined the team. And you can also join the team if you think that you can make something like this work or if you want to help on that. There's a lot of things that need to be done. Also, especially if you have a lot of experience and time for managing projects like these, you're definitely welcome. So yeah, that's the plan for the flight controller for now. And that's the progress we made the past week. In the meantime, Cluster has been trying out different OpenVSP designs to get familiar with how it works and how to do the calculations that you saw in the last video. Right now, he's basically trying a bunch of different models like this one, for example, but also the one I found so ugly from like the first video. I said this was ugly. Well, we're trying it out and seeing like how efficient this is. We're basically only focusing on horizontal flight because vertical flight is just adding some propellers. So sure, I mean, this will do worse in real life. So we will have to test things in real life or in CFD, but we'll see. So this is just kind of going on in the background as well. Now, I do have another thing or plan that I kind of want to work out because we need to think about how we're going to structurally build the airplane. Okay, imagine that this is our amazing plane with a jet engine for some reason. Doesn't matter, okay? It doesn't matter. So of course, we need to have a structure inside of this plane. Now, like I said before, I kind of want to have a styrofoam mold. Let me tell you more specifically what I'm imagining for a styrofoam mold, okay? So this is the plane. We want the outer layer to be styrofoam. So this should be styrofoam. So then you basically just make a mold for that shape. Something like this, for example. And you would have holes at some places where you can enter in a mix of 2-component styrofoam, like I don't know what it's called exactly, but when it mixes together, it turns into styrofoam and it can expand up to 20 times. Now, maybe if we do this and we don't let it expand 20 times, then maybe it'll be like more dense and more strong. But either way, we cannot really depend that styrofoam gives us any strength, of course. So we kind of need to think about the frame, the airframe of the entire drone. So what I'm basically imagining is like underneath the styrofoam layer, we can have an entire frame, just entirely. Now, of course, maybe this seems like it would be very heavy, and I would agree with you. But we could do things like the main level, like the middle part, the bottom. We could make this like a proper aluminium frame, for example, and just make that go around the whole thing, as aluminium is fairly lightweight. And then when you have this aluminium frame there, you can basically make this section around it out of something else, and I don't know what. So I'm just going to think that out real quick, and then I will get back to you. All right, I'm sorry for the terrible, chaotic explanation that I gave back here, but I actually made it in Blender and I'm quite proud of what it looks like and I think it could work, so I'll show you. So this is the outer styrofoam part, which basically you can make like with a mold like this. I modeled it real quick with an internal piece. So this is a hole to show you what goes on inside. So it's just like a mold basically, obviously. And then you get this styrofoam piece out of it, like this, as you can see from the inside. And then as a frame, you just got this, and this could be 3D printed, and it has a bunch of holes in it to save weight basically. And you just slide the styrofoam piece on top of it, and I think that that could make it pretty strong while still being pretty lightweight and pretty cheap. I mean, as long as this is cheaper than carbon fiber, then I think we're doing the right thing. And it looks like it is a pretty good solution, not gonna lie. Well, 3D printing this could take a long time. For some people, it is interesting to do. But this can also be made out of things like aluminium or I don't know. So I'm going to ask Jordy to make a test like this in a small scale, and then I'm going to 3D print a real version of this and try it out with actual styrofoam and stuff like that. So I'll tell you guys all about that next week. For now, I think we mentioned everything. I was not able to go into depth on a few other things. So, for example, Aryan made an entire list on different materials and densities. So this is going to be very useful in the future. But for now, we cannot really do too much with that. So thank you guys for watching, and I'll see you guys in next week's video. Also, be sure to subscribe to my Patreon because I still don't have a single Patreon. Oh, and I did make a bit of progress on the trailer, but it's still not done. All right, bye-bye.